This is the first video on section 4.5, tangent lines. And so remember when we were talking about lines in 3 space, we compared that to lines on the plane. For a line on a plane, you need a point and you need the slope. And we talked about how the slope could be represented as a vector, or the slope was just the number representation of a vector which gave the direction. A line in 3 space needs a point and it needs direction. And so we're going to find the tangent line to vector valued functions at a specific point. What do we need for a line? We need a point and we need a direction. And in Calc 1, we learned that the derivative of the function at a point gave us the slope. And in Calc 3, we're going to learn that the derivative of a vector valued function at a point gives us the direction of the line. It gives us a direction vector. And so, for example, r of t is t to the 4th, t squared plus 1, 4. We want to find the equation of the line that's tangent to this curve at the point where t is equal to 2. So we calculate the derivative of r. It's just 4t cubed, 2t, 0. We just take the derivative of each component function. R of 2, remember we need a point. So we have to substitute 2 into the original function. That gives us the vector 16, 5, 4. And then we substitute 2 into the derivative. That gives us a direction vector, 32, 4, 0. Now remember, we just need direction. We can factor a 4 out, and we have the vector 8, 1, 0. The vector 32, 4, 0 and 8, 1, 0 are parallel vectors. They have the same direction. They have different. So this vector is equal to this vector. But if I ignore the 4, so the vector 32, 4, 0 and the vector 8, 1, 0 have the same direction. Different magnitudes, but the same direction. So we can go ahead and use the vector with the lower coefficients. And so I'm going to give you the 3 different versions of the equation of the line, the parametric equation. So we have the point 16, 16, 5, 4. That is our point. And then we have our direction vector is 8, 1, 0. So the parametric equations, x is 16 plus 8t, y is 5 plus t, and z is constantly 4. Z is 4 plus 0t, 4 plus 0t, which is just 4. For the symmetric equations, remember you solve for t for the parametric equations. So we have x minus 16 divided by 8 is equal to y minus 5. We solve for t right here, and we don't have a t, so we just write z equal to 4 alongside this equation. And I put it below because I'm running out of room. And then the vector equation. We have the point 16, 5, 4 plus t times the vector 8, 1, 0. So we have a point and a direction. These are 3 different versions of the same line. When you're doing these problems on your own, you only have to give me one type of equation, whichever one you like the best. Part B is very similar. So we have our vector function t cosine of pi t e to the t. And we want to find the equation of the line that's tangent to the curve at the point corresponding to t equal to 1. Calculate the derivative of t, derivative of cosine pi t. We use the chain rule here. The derivative of e to the t is e to the t. We learned that in Calculus 2. What is r of 1? Because we need a point. R of 1 is the point 1 cosine of pi, which is negative 1, and e to the 1, which is e. What is r prime of 1? This is the vector we're going to use for our direction vector. R prime of 1 is going to be 1. Sine of pi is 0, so we have 1, 0, e to the 1, which is e. So the components of this vector give us the point in 3 space. The components of, or this vector here is the direction vector of our line. So remember, we need a point and a line. So we take this vector here and we interpret it as a point, basically. We look at the point whose coordinates are the components of this vector. We use parametric equations here. X coordinate plus t times the x component. Then we have the y coordinate plus 0 times the t. And then we have the z coordinate plus t times the z component. So this says e as a number times t. This is not e to the t that we're used to writing. So we're used to writing e to the t. But what this says is this is e the number multiplied by t the variable. So it's not e to the t, it's e times t. For the symmetric equations, again, solve for t. So here we have x minus 1. Here we have z minus e divided by e, and here there's no t, so we just have y equal to negative 1 by itself. And then the vector equations start with our vector 1, negative 1e, plus t, our parameter, times the direction vector, 1, 0, e. So again, for the equation of a line, we need a point and we need a direction vector. To get the point, we substitute it into the function we're given, just like we did in Calc 1. And to find the direction of the tangent, we plug the number into the derivative, like we did in Calc 1. It's just a little bit different because we're dealing with vector valued functions instead of real valued functions.